All right, so I want to show you some examples of more advanced examples of how to solve problems. These will involve kind of more complicated situations. They might involve things from other units. So here we have an example of you're walking by a pond, you find a rope of length L attached to a limb of a tree. It doesn't say tree, to a tree limb. And so you are going to have like some sort of situations. There's like a pond and there's like a tree with some sort of limb, whatever. Who cares about what it looks like? There you go, tree, limb, and there's some sort of rope hanging from it, okay? And maybe it's like something like that, so you're not gonna be kind of touching the water idea. And it's basically saying you're gonna start with an initial angle of theta 0 from the vertical. So you're gonna have some sort of initial theta 0 where you're gonna grab on and then you're gonna swing. So when you swing, you are gonna make a circular arc, just like if you were a pendulum or something. So you'll kind of be at different points. And you have a known mass, and we want to know what is the maximum tension during the swing. So where would that maximum tension occur? Well, that maximum tension is going to be related to your speed. And it's going to be related to your centripetal force. So if you think about the vertical circle example that we did previously, I think it was in our first day of circular motion, when we looked at different points along the swing and kind of what's going on, like with our forces, you know, we had gravity and tension here, and we said like on the sides, your tension was your centripetal force. You're probably not going to swing in a circle through the top, so it's probably not the top, but your gravity and your tension were both pointing down, so your centripetal force was the sum of tension and gravity. And over here, your tension force was your centripetal force, and down at the bottom, since gravity was pointing out, and your tension force was pointing up, our centripetal force was tension minus gravity. So in this case up here, if we were to solve for tension, our tension is going to be our centripetal force minus our gravitational force. So basically tension is related to our centripetal force and our gravitational force, which is constant. So the bigger my centripetal force, the bigger the tension. But if I look down here at the bottom, my tension force is equal to my centripetal force plus gravity. So if I had the same centripetal force in both of those locations because I was going at a constant speed, my tension would have to be higher here because it would be that same centripetal force. Okay. Well, if this is a real circle and I could make that circle, would my centripetal force be the same? Well, no, because I wouldn't have something able to control it. Gravity would be what's driving my motion. So, and if you think about it, and you think about energy, and this is a very energy related type topic, if I were to start at some angle here, my speed is, let's say I started here, my speed is going to increase as I move down here. I'll be moving very fast here. Remember, our centripetal force is AC, which is V squared over R. So the faster I'm moving, the faster my centripetal force. As I move up in the circle, if I could continue doing that, I'm going to slow down, and I'm actually going to be going slowest at the top. So my centripetal force is most likely going to be smallest at the top, making this term up here even smaller for tension. I don't need a very big tension. Remember, the minimum speed at the top to go around would actually be no tension. So, in that case, that tells us very clearly that at the bottom, even if I was making a full circle, the bottom is where my maximum speed is going to occur, and the bottom of the arc is where my tension is going to be the largest. So now that you know that tension is going to be large at the bottom, that actually saves a bunch of time. But going through that's really important thought process. So basically what we're looking for is we're looking for the tension at the bottom of the swing. So let's take a look at the bottom of the swing. Well, if I was looking at the bottom of that swing, kind of in terms of forces. So once again, thinking about our forces, we'd have our gravitational force pulling down and our tension force going up. I'm drawing my tension bigger than my gravity because it needs to be. Then remember that my centripetal force is going to be my tension minus my gravity at that point. So what I'm looking for is I'm essentially looking for my maximum tension. And in order to do that, I'm going to have to know some information about my centripetal force and my gravitational force. Well, my gravitational force is pretty easy because it gives me my mass, so it's going to be m times g. Well, what about my centripetal force? Well, if I sub in, my centripetal force is going to be MAC, and AC is going to be V squared over R. Really what I'm looking for is I'm looking for my maximum speed. Whatever that maximum speed there is, or whatever the speed really is at the bottom of that arc, is going to be the speed it's going to give me my maximum tension. And then it's going to be plus m times g. Now, the radius of my arc is going to equal the length of that rope. So I can replace my radius r with length. Kind of right off the bat. So the only thing that I don't know is this maximum speed. Well, how can I find that maximum speed? We need to go back to energy. Doesn't tell you about energy, doesn't say to use energy, but that's really the only thing we can do because we have a conversion of potential energy to kinetic energy throughout that swing. And I can figure out how much potential energy I have initially. So if we take a look kind of at this arc as it goes between these positions, I have position 1 here and I have position 2. So if I set up kind of a coordinate system here, I'm going to define that my h is equal to 0 down here at the bottom of the arc and assume that's the lowest that I can go. And this is going to be a height of h here. Or I guess this would be y equals 0. Sorry. This would be like y equals h. So I'm going to travel through a displacement of h would be my change in height. And at this point, and I'm starting at rest. So I'd have no kinetic energy at that point. And my potential energy would be mgh. Here at the second point, my kinetic energy would be at a max, and it would be 1/2 mv max squared. So that's the speed I'm looking at there. And then, but my potential energy at that point would be equal to 0, I guess K2. K2 would be equal 1/2 mv max squared. So I have conservation of energy, so K1 plus U1 is equal to K2 plus U2. But I'm defining K1 to be 0 and U2 to be 0. Please remember to always show this step. Even this far throughout the year, I still find people not showing this step, and this is a very, very important step. I know it seems obvious, but it's a key. And then mgh1 is going to be 1/2 mv max squared. Notice that mass actually cancels out from this part. And if I multiply the 2 over and then take the square root, I get V max is the square root of 2g h1. But oh wait, I don't know h. I don't know my initial height. Well, what would that be? Oh, we've done this before with pendulums. So remember that we have the length of the string L here. I know my initial angle theta 0. H is this portion right here. If I call this x, then remember that if I have this triangle, that x is going to be L cosine of theta 0. And I know that this total length right here is also the length L. So L is going to be, so H is going to be L minus x, which is L minus L cosine theta 0, which is L times 1 minus cosine theta 0. So we've done that before, so that's just a reminder. So we can sub that in up here. So we get that V max, actually, let's just leave that as V max squared, because I noticed that's a squared there. So I'm just gonna leave that as V max squared is 2gh1. So V max squared is gonna be 2g L times 1 minus cosine of theta 0. So I can then go back in up here and plug that in. And I get that Ft max is going to be m over L times 2GL times 1 minus cosine of theta 0 plus mg. And I find here that actually the L cancels out of the equation. So the length of the string doesn't actually matter at all. The mass still does. Mass matters a lot because the bigger the mass, the more tension you're going to have pulling on it. So I get Ft max is equal to 2mg times 1 minus cosine of theta 0 plus mg. So basically this tells us that the bigger the mass, the bigger the tension is going to be at the bottom, and you can kind of go from there. You can analyze the fact of the effect of the angle if you wanted on what happens and so forth. All right, so this next question is a really good example, kind of combining some different concepts. So the maximum speed a 2,000 kilogram car can go around a curve with a radius of 50 meters without slipping is 10 meters per second. So what we're assuming here is that if I was looking from like the top view, that we have a perfect circle here with a radius for that curve, like very non-perfect. So like if the car was here, it's moving with some sort of speed. That speed is 10 meters per second, and that's the maximum speed I can go without the car slipping. So if I look at that from like a side view, and so I can kind of think about what forces are in play. If it's a flat curve, I'd have gravity here, and then I would have normal force. And then what would keep me going in a circle? Well, it's friction, because if there's no friction, I wouldn't be able to go around the circle. And it's actually a static friction force because we're talking about slipping. And we're looking at that maximum value. So what we're looking for kind of is Fs max at this point. So we're at that point right before we're slipping. If I go fast enough that my static friction force can't compensate for it, then I will travel in a straight line. And that's what happens you know, when people take curves too fast. And that's why there's lower speeds around curves, is to make sure that you stay away from that slipping point, because they don't want you curving off, you know, flying off the road straight because you've lost friction with the tires and the road into a tree. So how would we solve this problem? Well, we're looking for the coefficient of friction. So if we look at what's going on with this problem, the static friction force is going to be our centripetal force. Our static friction force would be mu s Fn, because we're at the point right before we slip. Our centripetal force would be mac, which would be v squared over r. That v squared is our tangential speed. That is that 10 meters per second. And my Fn in this case, because it's a horizontal curve, would just be equal to mg. So mu s mg is going to be mv squared over r. My mass actually cancels, so this is really interesting. It doesn't matter what the mass of the vehicle is. And that is good, because we wouldn't want to have a different speed for a semi-truck than we would for, you know, some little Honda something or another as we go around. And then we're looking for the coefficient of static friction, so mu s would be v squared over r times g. So notice that the coefficient of friction needed to safely go around is dependent on speed. The faster you go around the speed, the much higher the curve, the much higher your coefficient has to be, because of that squared relationship. Also, the bigger my radius of my circle is, the smaller my coefficient needs to be. So trying to navigate a tight curve needs a higher coefficient of friction than going around a very wide curve. So there's a lot of road design physics that goes into road design. So from that, you could plug in numbers, and we could get a coefficient. So our coefficient would be v squared, which is 10 meters per second, squared over a radius of 50 meters times acceleration due to gravity, 9.8 meters per second squared. And our coefficient would be 10 squared divided by 50 by 9.8, which would be about 0.20. So that's kind of a moderate value. Rubber between tires and so forth. It's usually a pretty high value. Some dings going off everywhere. All right, so we found our coefficient of friction. So that's going to be needed for later probably. So let's look at μs is 0.20. All right, so that's part A. Now, looking at part B, if the same curve was banked at 30 degrees, how fast can the same car go without slipping? So when we're talking about banking a curve, we're still talking about going in a circle with that same radius, but now with an unknown speed. But now we're banking the curve. So what that means is you're still making a circle, but it's banked. So this is kind of like a NASCAR track. So you're still making kind of a circular arc. Our radius here would be towards the center of that arc, but now you are banked. So, or if you don't watch NASCAR, think about the movie Cars. Okay, when it goes around the track, you know, it's curved. Why do they curve it? Well, they curve it because it's actually going to help so that you can go faster around the curve without slipping. That's kind of the reason. So let's look at our free body diagram here. Well, we're going to have gravity pulling down. We're going to have normal force pointing out, let's see. And then you would also have your friction force, and the friction force is kind of working the other way. I'm actually going to rewrite this one. I didn't think about this. That would make it really hard. Is actually do this without the aid of friction. They're not going to give you banked problems with friction. So this is without the aid of friction. Because I don't want to actually deal with friction. So what basically we're assuming is you could like grease down this track so that there's no friction between the tires and the road, and we want to know how fast we can make it around. So those are our forces because we're assuming there's no friction at this point. Our friction force would have to be perpendicular to the normal force. So it's going to be parallel to the plane, but it gets a little complicated because it might not always be in the same direction. So you have to like kind of think about that. So that's why we're not going to deal with that right now. This is sufficient. So 30 degrees here is our bank, so that's our angle theta. So when I want to think about this, I'm going to need to resolve my normal force into components. My gravity is perpendicular to my radius, so gravity is not responsible for being able to go around this curve. It's not helping at all. So I need to break my normal force into proper components, but I need to make sure I keep it in terms of the same 30-degree angle, that angle theta right there. So if I think about what's going on, this is going to be that same angle theta. So if I have a 90-degree angle here, then this angle is going to be 90 minus theta. And then if I look at, let's see, this 90-degree angle right here, then this angle right here is going to be 90 minus theta, which is just theta. So we're gonna make this angle right here theta. So this red angle is our theta value instead of this one right here. And if you use this, if you resolve the wrong triangle, you're not going to get the correct value there. So basically, we're going to look at our normal force. Move that around. And then I have here, that is Fn in the x direction, and then I would have Fn in the y direction. And it's my centripetal force is going to be Fn in the x direction in that case. assuming that there is no need of friction to go around this curve. So with that, I now want to find how fast can the same car go without slipping, without the aid of friction on this banked curve. And we get that our centripetal force is going to be MAC, which is mv squared over r. Our normal force in the x direction is going to be Fn, and that's the opposite side, so that's going to be sine theta. Our normal force is not equal to gravity, but our y component of our normal force is equal to gravity, because in the y direction, normal force in the y direction minus gravity has to equal 0. So although I don't actually know my normal force, I can find it, because normal force in the y direction, which would be normal force cosine theta, is going to have to equal my gravity. So if I can then solve for normal force is going to be mg over cosine theta. So I can take that normal force and plug it in here. So I get that mv squared over r is going to be mg over cosine theta times sine theta. Notice that once again, my mass cancels out. And if I solve for that speed squared is going to be, let's see, sine over cosine's tangent, so that's going to be rg tan theta, and then square rooted. So my speed is going to need to be the square root of rg tan theta. And if I plug in 50 meters for my radius, 9.8 meters per second squared for my acceleration, and tan of 30, I can find that my speed is about 17 meters per second. So this is really awesome. So around my flat curve with a coefficient of friction of 0.20, I was able to go 10 meters per second without slipping. On this banked curve with absolutely no friction, you end up with a speed of 17 meters per second that you are able to go around that curve without slipping.